Good morning, everyone. A couple announcements before we get started this morning. One is the first post-lecture assignment was due before class this morning. I noticed there's probably about a fifth of the class or so maybe missed the assignment or wasn't able to get into mastering. So I did bump the due date for that first assignment to tonight at midnight. So if you didn't get a chance to do the first homework assignment, you have until midnight tonight without penalty. And then the penalty is only a 1% deduction per hour late. So if you're close to the deadline, you get most of the points still. And the penalty only applies to the credit you earn after the deadline. And the last major thing to mention with the homework is there's a lag between finishing your homework set and the grade appearing in the Carmen grade book. So if you get like a 6 out of 6, and then you look in Carmen and see you have a 2 out of 6, it just updated after you did the second question and hasn't updated again since you finished the assignment. So there's about up to 1 to 2 hour delay in grades actually appearing in the Carmen grade book. Today's gonna be the first lecture with an attendance quiz. It's just gonna be, are you here? It's gonna be not really much of a quiz. It's just an attendance way of documenting who's here. It'll be through Carmen. It's a couple slides into today's class. There'll be a QR code that you scan. There's an assignment that you probably can't see in Carmen because it's not open yet, but as soon as I open it, you'll see it in Carmen. That's where the link will take you to. So there'll be a few ways to get to these assignments during class. And if you're watching this from home later, there's an alternate assignment that you can do. If you're here, you don't have to do the alternate assignment. It's a tutorial assignment on mastering chemistry. Probably will take 15 to 30 minutes per class to do the alternate assignment. If you'd rather do that than come to class, it's certainly your choice, but that's another way to earn attendance credit. It requires an upload, a snapshot. Look at the first lecture, has some info on that, but you will do the assignment, complete it, take a snapshot you can take a screen capture on your device or a picture with your phone, upload that to an assignment in Carmen, then I go adjust scores and fix them within a day or so after lecture. So again, you won't see those grades automatically appear, but you have to do a couple things, and it might take a couple lectures to get the system down, but we'll probably make some extensions if needed for those too, just to make sure everybody understands those policies as we continue into the course. And so the last thing to mention is lab. I think most labs meet tomorrow. Did anybody have lab on Tuesday? Okay, so I think all of our labs meet on Thursday in this class, but make sure you have your lab coats. If you didn't get them yet, Celeste, I think it's 170 Celeste, back of the first floor. There's a stock room where you can get them from. And then make sure to have pants. If you're not wearing pants tomorrow or not planning on, just bring a pair of sweatpants. And then make sure you have closed-toed shoes. They're supposed to have a heel on the back. Those sort of details. So make sure to wear proper lab attire, and also check out all those lab announcements. If you're stuck on anything, 205 Celeste is a great place to get help with lab questions throughout the semester. And the 205 help room, 205 Celeste is in the middle of all of our labs on the second floor. If you haven't been up there yet, you'll see it soon. It's open 10 a.m. to 3 p.m. Monday to Friday. Okay. So with that, let's get back into chapter 1. We were talking a little bit about this slide before I kind of started jumping ahead to wrap class up on Friday. So let's come back to this slide and kind of introduce it from the start. There's metric prefixes that I want us to be able to use throughout the semester to make conversions between like centimeters and meters, millimeters and meters, milligrams and grams, milliliters and liters. So I want us to be able to use the prefixes to make conversions throughout the semester. Some of these are on the smaller side, so the centi, milli, micro, and nano are for converting units that are generally on the smaller side. And so the centis, 10 to the minus 2, milli, 10 to the minus 3, micro, 10 to the minus 6. And we'll go up to nano that we expect you to know through nano. You can look up femto and pico and continue, but we're not going to expect that you have those memorized beyond the nano prefix. And let's just remember that the way this would be used is that, let's say in terms of meters, 1 meter would be equal to 100 centimeters, or you could say that 1 centimeter would be equal to that 10 to the minus 2. So 10 to the minus 2 meter. And if you're sure of one of those two conversions, you can get to the other. So the difference between these two conversions is just dividing both sides by 100 from, say, the first conversion, or multiplying both sides by 100 for the second conversion. But you can always say how many centimeters are in a meter, or how many meters are in a centimeter, and you can just think centimeter is small, it's on the smaller side, so it should be 10 to the minus 2. Just in case it's been a while since we've seen scientific notation, we'll make sure to mention and review some things with scientific notation. That 10 to the minus 2 would be 0.01. If we go millimeters, 1 millimeter is really small. It's 10 to the minus 3, so this is a 10 to the minus 3 meter, or a 0.001 meter. And then, of course, you could say that 1 meter would have a lot of the millimeters. So if we multiply both sides by 1,000, then we'd have 1 meter is 1,000 millimeters. So I just want us to be able to make conversions using these metric prefixes throughout the semester. Some of the prefixes are on the usual side for things that are larger. So giga, mega, kilo, these are for things that are generally on the larger side. 10 to the plus 3 for kilo, 10 to the plus 6 for mega, 10 to the plus 9 for giga. And so giga, we usually gigahertz is usually a unit we think with the giga prefix, but you can think a kilo anything would be 1,000 of that thing. So if I have 1 kilogram, that would be 1,000 grams. 1 megagram would be 10 to the 6 grams, which is of course a million. A gigagram, which probably isn't the most common unit to see, a gigagram would be equal to 10 to the 9 grams. And we could use grams, meters, liters, hertz. Maybe hertz isn't a great unit to use because we don't maybe know what it is yet in this class in the context of units, but it's just whatever that symbol is, you just apply the prefix accordingly. Okay, let's just do a couple conversions. So let's take 0.000125, so 3 zeros, 125 seconds into the given units. And some of these units don't make much sense to convert to. Like, it doesn't really make much sense to convert this quantity of seconds into megaseconds, but let's just do it to make sure we can do the conversion. And so if we're taking, and also this kind of gets into the very last section in chapter 1 is using dimensional analysis, which is a way to convert units or way to solve problems involving units. So we'll use dimensional analysis. So I'll set up a dimensional analysis problem where I start with what I'm given. I did miss a question before on converting it to scientific notation, so we'll come back to the first kind of point in a minute. But then our conversion into megaseconds would just be that 1 megasecond. My thought's going to be, I should either think how many seconds are in a megasecond, or how many for 1 second, what would that be in terms of a megasecond? And so depending on the conversion, depending on the situation, I think it's easier to remember that 1 megasecond would be a lot of seconds. Yeah, because the main way to mix this problem up is to put a minus sign in here accidentally. Like if I say 1 megasecond is 10 to the minus 9 seconds, let's think what that would mean. That would mean that 1 megasecond is very small, or a very few number of seconds. And that's not the case. A megasecond should be a tremendous number of seconds. It's 1 trillion seconds. And so as long as I'm thinking big unit, a lot of seconds, everything lines up accordingly. And if I wanted to flip this around, it would be 1 second is 10 to the minus 9 megaseconds. If I want to divide both sides by 1 trillion, I could use that conversion too. I'll write it over here. I could have said that 1 second is 10 to the minus 9 megaseconds. I don't think it's that intuitive to use that conversion factor in this problem though. But if you're thinking that, well, could we say how many megaseconds are in a second? We could. It's just 10 to the minus 9 now, because 1 second in megaseconds is very small. So a megasecond, big unit, a lot of seconds. 1 second in terms of megaseconds would be a fraction of a megasecond. Okay, so if we do this math here, I think I have a normal calculator. And let me, unless I'm taking my normal calculator out, but I'll just use my iPhone calculator. Remember, for exams in the class, you're going to need specifically a TI-30, a TI-83, or a TI-84 calculator. I know it seems crazy, but there's a lot of calculators that don't have those numbers. We really need them to be those specific brands. Yeah.
Why is 9 and not this?
Oh, yeah. Yeah, good catch. Yeah, I used the giga conversion. Thank you. Probably half the class was, or more, was thinking I was insane because I just have it right here. I was using the giga, and I should be using the proper mega conversion. Good catch. So just taking that and then dividing by, and again, it may have been a long time since some of you guys have even used a calculator. I don't, like, sometimes we take chemistry and physics early in high school or senior year. We don't do a lot of calculations. Let's remember how we put 10 to the 6 into a calculator. So when we're putting 10 to the 6 in the calculator, one of the common mistakes I sometimes see is people use 10e6. Why would this be wrong? What does this mean? If I write this into my calculator, what does that mean? That would be 10 times 10 to the 6. And so this would be the symbolic for 10 times 10 to the 6, because e to the 6 is times 10 to that power. And so this would not be how we'd want to enter 10 to the 6. 10 to the 6, we either go 10 caret 6, or we can go 1e6, is how we would enter that into the calculator. So I got 0.000125. I'm going to divide by 1e6. That's how I usually enter it, because I usually have a harder time finding the caret or the power button on a calculator. And so what we want to enter is 1e6, because that would be equal to 1 times 10 to the 6. And that's what we want to divide by, is 10 to the 6. Now, when I get a bunch of zeros, if I want to force a calculator into scientific notation, something I can usually do is find the scientific notation button. Sometimes it's easier to find on a normal calculator. So if I had like a scientific calculator, I'd be looking for the floating versus the scientific versus the engineering mode. And I could change it to scientific mode. If you had a TI 83 or 84, it would have already popped out in the scientific notation mode. And so then on the iPhone, I guess it just shows you here in scientific notation. On the big screen, it shows you all the zeros, but that would be 1.25 times 10 to the minus 10. So let me rewrite that a little bit bigger. So 1.25 times 10 to the minus 10. And that would be megaseconds. So again, it doesn't make much sense to convert it to this unit because it's such a small number of megaseconds, but just showing how to make that conversion. Let's also then address the scientific notation point that I missed on the first part here, where we're just trying to convert this into seconds, but in scientific notation. And that's just where we go 1, 2, 3, 4. So this would be 1.25 times 10 to the minus 4 seconds. And then had we done it in scientific notation first, or seeing that the number of seconds is 1.25 times 10 to the minus 4, dividing by 10 to the 6, you may remember that'll drop it by 6 orders of magnitude. And so when you see minus 4, take 6 more away, and then that gets us to the minus 10. So you may have been thinking, can I use exponent math? If you're thinking that, yes, you can, and you could have gotten there pretty quickly, maybe if we started in scientific notation. Okay, so now can we convert the number of seconds to microseconds? So I'm going to start with the number in scientific notation. And then I want to use the conversion to micro. So micro's 10 to the minus 6. And so what conversion do I want to use here? So let's use 1 microsecond, or let's put it in the right spot. So 1 second is where I'll start here to convert seconds. And now second is a lot of microseconds. So this will be 10 to the 6 microseconds. So a lot of microseconds in a second. Remember, the easiest way to mix up this problem is to put the minus sign in the wrong spot. If I put 10 to the minus 6 up top, then I'm making a mistake, because that would be making it seem like a microsecond was very big. The microsecond's very small, so there's a lot of microseconds in a second. And so this should go to 1.25 times 10 to the 2. If we think of the exponent math, you may not be thinking that way, but one of the easy things to do is just throw it into a calculator if we're not sure. So 1.25, if we can find the EE button, e to the minus 4, and then times 1e6. So I get 125, or 1.25 times 10 to the 2. So I'll just write 125 seconds. Nanoseconds, basically the same conversion, but 10 to the 9. So 1.25 times 10 to the minus 4 seconds. And this 1 second is a 10 to the 9 nanosecond. So minus 4 plus 9 should be plus 5. So it should be 1.25 times 10 to the 5 if we're thinking exponent math. Again, that's You always have access to a calculator for exams. So I usually say, if you're not sure of the math or if it's a relatively easy to mistake math step, just throw into a calculator on a test so you don't make a simple error. But I go times 1.25 e to the minus 4 or 0.000125 times 1e9. Now I could go 1e9 or 10 caret 9. So I get 125,000, and I'll go 1.25 times 10 to the 5 seconds. Oh, times 10 to 5 nanoseconds. Let me properly write the units in. So we're converting these to microseconds and nanoseconds, and I mistakenly not included the proper unit. So writing in microseconds for that next to last example and nanoseconds for the last example. Okay, so again, we just want to be fluid with converting using these metric prefixes within problems in this class. So be expected to use these conversion factors. When you need non-SI conversion factors, when you need to convert like liters to gallons, we'll give you that conversion factor. If you need to convert ounces to pounds or something like that, we'll give you those non-SI conversion factors. The only conversion factors we really expect that you have memorized are these conversions from like milliliters to liters, et cetera, using these prefixes. Okay, so with that, let's talk temperature for a minute, just to introduce and make sure we're familiar with the Celsius scale, which I think most of us are, and also to introduce the Kelvin scale. We'll use the Kelvin scale a little bit later in the class. We probably won't talk too much about Kelvin temperatures until chapter 5 and then later in chapter 10. But just to introduce those scales here, we have a couple of conversions. Let's look first at these ones, the Fahrenheit to degree C conversions. And so if we take a Celsius temperature, we multiply it by 9/5, add 32. That's how we convert to Fahrenheit. And if we have a temperature in Fahrenheit that we want to convert to Celsius, you could either A, start with this equation here and do the math on it to change it into calculating the Celsius temperature, or just use the provided equation that we take the Fahrenheit temperature, subtract 32 from it, and then for that quantity, multiply it by 5/9. That'll give us the temperature in Celsius. And then if we have a temperature in Celsius, we can convert to Kelvin. Kelvin's really useful because it's an absolute temperature scale. Temperatures can't go below 0, so it establishes a 0-point minimum so we don't have negative temperatures. And so that's when Kelvin's used, when we need what we often call an absolute temperature that can never go negative. So that's our Kelvin scale. We take our Celsius temperature and add 273.15 to it because the lowest temperature is negative 273.5 degrees C or 0 Kelvin. So if you take negative 273.15 as your Celsius temperature, add the conversion factor to it, that gets you to 0. So we're not going below negative 273.15 degrees C for any substance in the universe. Okay, so let's do a couple conversions just so we can convert between the units. And also let me mention, I wouldn't expect that you have these conversions memorized. We give you these conversions if you need to use them on exams. Every now and then I get questions a lot on what equations or conversions you get with an exam. We usually look at an exam and give you the conversions and equations you need for that exam. We usually don't make just a general chart of all the things we would give you if you ever need them. I give you something similar to everything you might ever need in the daily quiz area. So if you go to daily quizzes, there is a chart there, and the things that you would tend to get when needed are indicated on that chart. So you can kind of see a chart that you can have some good idea of what to expect on exams. But just know when we write an exam, we just won't give you the things you don't need. So we only give you an equation sheet based on an individual exam for what you need for that exam. So it's a little bit kind of hard for sometimes you guys to figure out what you get with exams, but look at the daily quiz area. It's a module in the lecture area. Okay, so let's convert 77 degrees Fahrenheit to degrees C. So we're just gonna throw 77 into this equation here. And so we take our degree C temperature would be 5/9 times 77 degrees Fahrenheit minus 32. And so that works out, 77 minus 32 is 45. So 45 times 5 divided by 9 works out to be equal to 25 degrees C. So kind of standard temperature, like a normal temperature, 25 degrees C is a slightly stuffy room. So if you've ever wondered, 25 degrees Celsius, sometimes we take that as kind of like normal temperature, is slightly warm in a room, so 77 degrees Fahrenheit. And then if you want to convert 25 degrees C to Kelvin, so to convert to Kelvin, we have to have a degree C temperature. So we convert Fahrenheit to degree C, and then our temperature in Kelvin would be equal to the degree C temperature, and then plus 273.15. And that'll take us to 298 Kelvin, which also then takes us into a topic of sig figs on like why we might round things where we do within calculations. So we'll see sig figs in a moment, but let's think if I had 25.00 degrees C, then I would keep the 0.15. And we'll talk about rounding rules in a minute, but we're gonna see that we're gonna round this off to 298 Kelvin. So we need to get into sig figs to kind of see why that is. But just know that our conversion here is just due to sig figs. That'll be our next topic of discussion. Okay, so again, for temperature scales, I just want us to be able to convert with equations when needed. And then one thing that I want to mention is the degree C and Kelvin scale have something interesting in common, that a 1 degree C increase in temperature, if I go from 25 to 26 degrees C, that would be 298 to 299 Kelvin. So a change in temperature in degree C is the same magnitude as the increase in degree C. So we can see that here, 0 degrees C, melting point of water, 273 Kelvin, boiling point of water, 100 degrees C, that's up 100 Kelvin. So there's a 100 Kelvin difference between 0 and 100 degrees C and between 273 and 373 Kelvin. So an increase in temperature is incrementally the same magnitude in Kelvin as Celsius. So that's worth seeing. We'll revisit that in chapter 5 and talk about when that applies to some problems as well. It'll apply to problems where we're calculating delta T's and trying to make sure that a delta T in degrees C is the same as a delta T in Kelvin. So we'll revisit that later. But then notice that we get different increments in Fahrenheit. So the Fahrenheit difference between the boiling and freezing of water is not quite 200 degrees Fahrenheit, so it's a different scale, different increment. So a different increment or change in temperature in the Fahrenheit scale. So just wanted to point that out as well. Okay, so let's get back into this topic of significant figures. We were kind of scratching the surface, I think talking slightly about this at the end of class on Friday. I think it's a little bit unfortunate. One of the lab assignments was getting into sig figs over the weekend that you guys had to do because we hadn't yet had a chance to even have a third lecture yet to talk about some of these details. But let's get into the conversation here. So when we look at a number, the digits in a number are what we're calling significant, or what give the number some significance. So when we see a number like 1.25 grams or 1.05 grams, each of those values has the same significance of having 3 total sig figs. And so those have 3 sig figs. But if I look at a number that's like 0.25 grams, now this number here only has 2 sig figs. So it has a less degree of precision than the other values did. It's good to the same placeholder. So all these measurements are good to the hundredths placeholder, but the one only has 2 sig figs because the 0 doesn't count as a sig fig. It's just like a leading 0, we call that. It just kind of starts the number. So we don't start counting digits until there's a non-zero digit, and then we count all the digits like after the decimal place. But let's talk about a few sig figs that come up when we look at a number like 125,000 grams. When we see a number written this way, we don't really know too much about the significance of these zeros here. I don't know if those zeros are intended to be significant or they're insignificant, but we generally are not going to count those zeros as being significant and only take the 3 non-zero digits. So when we see a number without a decimal point, then the zeros after a number, so like these zeros here, are not zeros that we count as being significant. So this number here would only have 3 sig figs. Now let's come to an idea that the sig figs are telling us where the plus minus, they're telling us where the inherent uncertainty in the measurement lies. Whenever we see a number like 125,000, we're thinking that this would mean 125,000 plus or minus at least 100 of units in that number. Like that's where the uncertainty is lying. If we wanted to imply that we had a greater precision, we maybe measured this mass with a better balance than only capable of measuring to the nearest 100 of a gram, then we might want to use scientific notation. So if we saw a number like 1.250 times 10 to the 4 grams, then the simple writing of that 0 would tell me that it had to have been significant. Like if you're reading a number off an instrument panel and you see a 0 on the instrument, if you're in the lab measuring a balance and you see a mass is like 1.250 and you see the 0, it's significant. That's why it's on the device. And you might even see that last digit kind of waffling a little bit, going up and down. And that's kind of showing you that the last digit on any instrument has some inherent imprecise or uncertainty about it. So we often call the last digit, let me use red here. So the last digit in a number, I'll underline in all of these in red, is what we call the uncertain digit. The uncertain digit is the one that has some inherent uncertainty, and that's what's leading to this topic of significant figure discussion that we're having here. And that uncertainty is going to be what leads us to then start rounding off math problems when we start doing math with these inherently imprecise or uncertain values. And so let's circle back to a discussion that when we're looking at these numbers, that we're thinking of them as being some inherently measured quantity in a lab with a tool. We'll do a demo here in a minute that'll kind of show us, depending on the type of instrument or device that we use, we might get more significant figures or less significant figures than other ways that we can measure quantities. And it's all about how certain do you know something is, so that when you make a change or do a calculation, how well do we know the result of that calculation? Where do we need to round it off to? So that's when rounding, we have to sort of pay attention to sig figs so that we don't either overstate the accuracy of our results. This is like when you throw 1.25 divided by 0.11 into a calculator, and let's say that's mass over volume or whatever, and you get like 10 digits. You don't want to report the 10 digits. There is a certain number of digits that are actually going to be required, or that are going to be precise enough to report with our values, and we're going to round off to that value using some significant figure rules. Okay, so let me do this demonstration here. Let me switch my screen over. Okay, so I have two pieces of metal here, and I have 3 scales. And the kind of thought is, if I want to take the length of one of these pieces of metal here, and if I use the first scale, like, do you see how it's not quite to 10? It's definitely not 5. It's somewhere between 5 and 10, very close to 10, maybe 9, 9.5. Do you see how I'm kind of, I would have a hard time kind of figuring out what the length of this object is with that first scale. And so depending on the scale, I may only know the length of that object to about 1 sig fig. So maybe I'm only going to be able to say, based off this measurement here, it looks like it's about 9. I think this is centimeters, so let's say it's 9 centimeters. So I'm using, scale 1, and I get it to be 9 centimeters. And I could probably tell it's a fraction over 9 too, but I just can't tell how much over 9 it is based on the scale. So then I say, well, I find a better ruler, so I take a different ruler, I find a new scale, and so then I take the device onto the scale, line it up, and there I can see that it's actually well across 9.5. What would you approximate that as? Like 9.7 maybe, 9.8? If we're arguing if it's 9.7 or 9.8, like if you think it's 9.7, I think it's 9.8, that's showing us there's some inherent uncertainty in that tense placeholder. So with scale 2, we come up with a measurement that's about 9.7 centimeters with some uncertainty in that digit. Like that's a digit that we're having a hard time figuring with our scale. So we get a second sig fig with a different scale. And so then if I take the final scale, which has increments to the nearest tenth of a centimeter, and I get it lined up just right, I can see that that's 9.67. It's kind of right on the line of the 9.7, maybe a smidge. Let me see if I can even zoom in. I don't know how good the zoom is on this. Kind of hard for you guys to see. If you were up here, like it's like if you could see the line, it's like there's a line here, there's a line here, and it looks like it's right about here. And so I can interpolate that it's a little bit past the 9.7 mark. So this is the 0.7, that's the 0.8. So that's looking like it's about 9.72, 9.73. So I use my third scale, and I can pick up that it's about 9.72 centimeters with some uncertainty in that hundredths placeholder now. So depending on the scale I use, I can get 1 versus 2 versus 3 sig figs. Now imagine I'm doing a calculation then of maybe calculating the density of this object. So if I wanted to get the density of this object, I would need the length, width, and height. So I need to take the length times the width times the height. I need to maybe submerge it in water is another way to figure out the volume of this piece. Maybe need to figure out its mass. When I'm doing then a problem taking a mass over volume, I need to think, well, I'm probably only going to end up with 1 sig fig if I use scale 1 as part of my volume measurement. I'm probably going to get 2 sig figs if I use scales 2. If I use scale 3, I can probably get a 3rd sig fig out for my density calculation. So it's kind of like when we start doing calculations, we're going to have to truncate around our results more with scale 1, less with scale 3. It's all about how well do we actually know the actual length of this thing from the tools that we're using. Now, this object has some length. If I had a much better scale, maybe I can get this to 3 or 4 or 5 placeholders. But the key is I'm limited by whatever scales I use. I'm limited by how many placeholders I can write down confidently based on the device I'm using. And so we're going from 1 sig fig to 2 sig figs to 3 sig figs. So I more precisely know the value and the length of that object with scale 3. And so we were talking a little bit last time, I think, about precise. So being precise is the more digits I have in a number, the more sig figs, the more precise it is, the more precise it's known. And then if we actually then said, well, let's have some magical true length of the object, that's accuracy. Is the true accuracy, is the scale actually a proper scale, would be the next question. And maybe we would test that with some calibrated object. So maybe if we had an object that we knew was precisely 10 centimeters, we can line it up and see if our scale was perfectly 10 centimeters. So we could probably think about calibrating, and that's going to get at, is the actual method accurate? That's what accuracy is. Is that really the true length of this object 9.72 centimeters, rounding to 3 sig figs? Is that what the true length would be? Or is it some other number and our scale is actually miscalibrated? So precision is repeatability, number of digits, closeness to the to each other. If every time I put this on this scale, if I put this on here again, it would be a precise measurement too. If I can get the same length measurement every time I take the measurement, that's precision. And then accuracy, is that actually the true value? Okay, so let's think about this thought problem for an example. So if I were to approximate, there's I think 307 or 8 people in this class. Probably not quite 300 people in this room, but let's just say, for example, I look across the room and I approximate there's about 300 people here. And then the door opens and 4 people walk in. Could we say that there are precisely 304 people in the room? No. I mean, we'd have to go through the painstaking task of counting every single individual in the room and kind of holding still so we can get everybody's count in. And if we counted precisely that there was 300 people in the room, then 4 people walk in, then we can say there's 304 people. So that's really the issue at hand here, is that when we're approximating and we have a measurement that is only 300 plus or minus 100, it's going to take, think about how it's going to take at least 50 people to walk in the room for me to then have an approximation that there's about 400 people in the room to round to the nearest one significant figure. So we're going to need a lot of people to walk in the room with a really poor approximation. Maybe if I say it's 300 plus or minus 25 and have a slightly more precise measurement, then we can have fewer people walk in and know that there's an actual change in the count in the room in our approximation. So just think about how when we do math, we're going to have to be limited for that same reason. Okay, let's do our quiz here. So, and let me also switch back. Oops. Okay. So this, hopefully the QR code works. If you scan that, should take you into Carmen. If you're already in Carmen, you can just go to the assignments. I need to turn it on too. Hold on a second. The assignment isn't yet open, so if you're getting an error, it'll be open in 2 seconds. 10 seconds. Okay, it should be open now. It says quiz, and it's just, are you here? With one option, so it's not really a quiz. So it takes a code. If you don't see it on the screen, it's Adam, capital A. So generally, this quiz will be open for a minute or two when we take it in class and you find the code. You can either navigate straight to Carmen and be ready when it opens up, and I'll put a screen like this up and you'll have the code for the day. I'll leave this one open for a while just in case people have to look for it. But again, you don't need the link to get to the quiz necessarily. It just makes it easy for those in the room with cameras. But you can just navigate through Carmen, go to assignments, and then find the assignment for the lecture attendance for a given day. Okay, so I'll leave this open for the rest of the class. Normally, I would close it within a couple of minutes so that you have to be here in this time. It's silly, but I really want you to earn the points by either being here or by doing the alternative assignment. And so if you want to be at home during lecture, that's fine. Just plan on doing the alternate assignment. I don't want it to be easy for somebody to text their friend, hey, enter the code and just put your attendance in from home, because I really want you to be in the room to track the attendance. Okay. I think we're good on this slide here. Okay, so let's think about sig figs real quick on just counting the number of sig figs in a particular value. And let's also then think about when sig fig rules apply, because that's a tricky conversation. Sig fig rules apply to numbers that are inexact or uncertain and have some uncertainty about them. Not every number you encounter has uncertainty about it. For example, 100 centimeters in a meter, that's exact. That is not a rounded to 1 or 2 or 3 sig fig problem. There's exactly 100 centimeters in a meter by definition. So conversion factors are either very precisely known or given, or they're exact. And when we look at conversion factors, those are going to be things that we don't round our calculations off due to. Things we count. If I count 12 eggs, I'm not uncertain about how many eggs there are. So how many sig figs are there? There's an infinite number. Sig figs don't apply to the number 12 counted eggs. So if I say you have 12 eggs, and you do a math problem with the 12 eggs, you don't have to look at that as 2 sig figs. If I approximate that there's 12 eggs, then there's some inherent uncertainty. Then you would look at that as being some uncertainty. So the fact that I counted them, I know that that's precise and exact. And so another way of thinking here, instead of infinity, that's what I tried to write, there's the infinite sign, is that it's just an exact number. And so exact numbers aren't things that we're going to round off to 2 sig figs. Now, when I see 1.050 liters, so 105.0 liters, when I look at this number here, all 4 of those digits are significant. Now, the number after the decimal point would not have been written if it weren't significant. So that's the main idea there, is that this 0, this one here, has to be significant, otherwise it wouldn't have been written. And the idea is that we're looking at some ordinary unit. So we're imagining that this was some ordinary lab measurement that led this number to being determined, or it's representing that number as a measured volume. So this is a measurement, so it's subject to being an uncertain number. And remember that it would be 105.0 plus or minus at least 0.1 in that last placeholder. Has anybody taken a stats class ever? Have those who've taken stats, have you learned how to do, if you have an uncertainty and you're adding numbers, how to come up with the uncertainty is in the result? If you take a stats class, you can learn how to do the math of taking numbers, adding them or multiplying them, and doing the error analysis or propagation, or just the analysis of actually propagating what the plus minus would be on the result. Sig fig rules we're going to learn are a generalization of that more formal analysis. So just picking up that this is an uncertainty at least of 0.1 will help us understand why we're rounding things off, help us understand that it's that uncertainty. If you took a stats class, you can then very carefully see how that uncertainty tracks and do some math with the uncertainty. We're going to hide that math and not do that actual statistical analysis, but we're going to use some generalized rules of sig figs to help us round. Okay, the zeros that start the number off don't count as significant because they're just there to help us start the number. So the 0, 0 in front of the 305, those are insignificant numbers. We call those trailing zeros. If we turn this into scientific notation, I'd want to have the same number of sig figs. So if I turn this into 10 to the minus 2 grams, 3.05 times 10 to the minus 2, that has 3 sig figs. And then when I look at 0, 0, 305, that also has 3 sig figs. And I didn't specify above clearly, but 4 sig figs for 105.0, and then 3 sig figs for the 0.0305. So 3 sig figs for the 0.0305. The middle zero is nothing to be confused about. The middle zero here, that is always significant. If you're a zero between two significant numbers, of course that zero is as significant as it would be if it were a non-zero digit. So the middle zero there counts as being significant too. So 305, 3 digits there. Now, when we look at the conversion from inches to centimeters, usually you see this conversion given as 1 inch is equal to 2.54 centimeters. Sometimes you see the word exact given, and you should generally see the word exact given after exact conversions that are decimals, just so you know that that's an exact conversion. When I'm doing a problem here, like let's say I'm taking 25.25 centimeters, and I'm converting those to inches. And so the 25.25 number, that's 4 sig figs. And then I look at the conversion 2.54 centimeters to 1 inch. You might be thinking, okay, I see 1 sig fig in the 1 inch, I see 3 sig figs in the 2.54, and I see 4 sig figs in the value I'm starting with. What I see is actually, I see infinite sig figs or exact numbers here that aren't going to lead me to round. We're going to see the multiplication rule in a minute, but the multiplication rule is you keep the number of sig figs in the inexact quantity that had the least number of sig figs. So if we had 4 sig figs divided by 3 sig figs, we would round it to 3 sig figs. But it would have to be both of those numbers being inexact or uncertain numbers. I don't have that here. I have 25.25, 4 sig figs divided by a perfect number with an exact number. So I get 9.94. If I just look at my calculator screen, I get 9.9409 inches. And then I'm going to round this to 4 sig figs, so it'll be 9.941 inches. I keep all 4, because I'm taking 4 divided by a perfect, exact, infinite number of sig figs number. Okay, so conversion factors usually aren't going to make us round. It'd be weird if we round off for a conversion factor, because if that were the case, we should look the conversion factor up to a greater number of placeholders or look into the conversion factor. This conversion factor here is exact, so we don't round off to 3 sig figs. And again, we're getting ahead a little bit. We haven't seen the multiplication rule, but we'll see that on like the next slide or two. So the conversion here, both of those numbers have an exact number of sig figs. They're both infinite number of sig figs, so it's like 1 inch with an infinite number of zeros, divided by 2.54, followed by an infinite number of zeros in terms of how we treat that mathematically with our sig fig rules. Now we have a burette. You'll use a burette, I think, in lab. First week or two you're in the lab. A burette actually this looks more like a graduated cylinder. Usually a burette has an inverse. Usually a burette has a high number on the top and you drain it to 0. A graduated cylinder usually starts filling in this direction here. So if I'm measuring from 86 to 85, so this would be 85.1, 2, 3, 4, 5, 6, 7, 8, and then I see this meniscus is between the 85.678 and so 85 point, somewhere between 85.8 something to 85.9. So that's where our measurement is. It's between the 0.8 and the 0.9. And what do you guys think if we zoom in? Maybe 0.5 here. Like we can probably say that it's 85.85 milliliters. Is that reading? You see how I can interpolate between my scale markings? And then you might argue, you might be thinking it was 0.4, maybe you thought it was 8.4, maybe you thought it was 8.6, maybe you think it's also 8.5. There's some inherent uncertainty. So you can kind of see that the digit that we last write down is the one that we have some uncertainty in, but we're more certain that it's a 4, 5, or 6 than it is like a 1 or a 9 or something else. And so that value still has significance. It gets included with the number. And so this comes up a lot in lab where you want to interpolate. If you have a scale marking and a measurement in between, try to use your best interpolation to interpolate if it's halfway across, a quarter of the way across, 3/4 of the way across. If you can see 0.4 versus 0.6 differently, you can go that way as well. Okay, let's get into the actual rules of sig figs so we can see how we do math. And hopefully this is pretty simple, but it becomes a problem. We're going to want to make sure we practice this because sometimes sig fig rules seem easy when we do an example or two in class. Make sure to practice these later. So the least certain measurement, the inexact quantity, that's the one that's going to lead us usually to round. So when we look at numbers, it's usually the one that has lesser digits or is known to the lesser, that's rounded to the higher quantity placeholder is usually the one that's going to make us round. So when we add and subtract, we're going to report results to the same placeholder. We're going to look at placeholders here as the value ending in the greatest value placeholder. Okay, so we just talked a lot about sig figs. What about placeholders? Well, placeholder would be like when we look at a number, would be like these placeholders here. So like the tens placeholder, the hundreds placeholder, the ones placeholder, the tens placeholder, the hundreds placeholder, the thousands placeholder. So those are like what I think of as being different placeholders. And so when I see a number that's like 123 like 1,000 versus a number that's 123, 405, say these are both grams, it's like that one's good to the ones placeholder. This is a greater quantity placeholder. So the 3 in the 12,300 is a greater quantity placeholder that value is ending in than when I have 1,200, 12,345. And so if I'm adding these numbers here, it's going to be this greater quantity placeholder. It's that plus minus being plus or minus 100 that's going to lead us to rounding more than the second number being good to the plus minus 1. Okay? So we're going to round the values to end in the greater value placeholder. So when I take 75 plus 75, it means I have ones placeholder plus ones placeholder. The result should be rounded to the ones placeholder, or should be reported to the ones placeholder. So that 0 is significant. Okay, so this number should be best written 1.50 times 10 to the 2 grams, so I can ambiguously show that that 0 is significant. Now, sometimes we get a little confused. Sometimes if I put this into a calculator, obviously it's a really easy problem. 75 plus 75, I just want us to have 150 in a calculator. You can then say, well, I thought you said the 0 is not significant in a number like 150. Well, you have to think context. If I just say in a different context, you have 150 grams of something, you're going to interpret that as 2 sig figs, and that 0 is not significant. That would be 150 plus or minus at least 10 grams. But this problem here, we got to 150 by doing math, and we have to think sig fig rules on this problem. And by sig fig rules, I found out that 0 is significant because the number should have 3 sig figs because of where the value needs to be reported to that ones placeholder. Let's think of a very similar problem. If I took 74 plus 74, what would that be equal to? 148. And that would be the proper 3 sig figs. If I took 76 plus 76, what would that be good to? 152 grams. So 75 plus 75, just because it ends in a 0 doesn't turn that 0 into an insignificant number. It's as significant as it would have been if it were the 148 or the 152. So we have 3 sig figs for all 3 of those additions. And then with the 150, we just may want to report it with scientific notation to unambiguously show that 0 is significant. And one thing that you can sometimes do is just put a decimal point there that kind of says, well, because I wrote the decimal point, I'm kind of saying that 0 is significant. That works sometimes when you're entering numbers into LabWrite. That was part of one of the activities, that you can just write the decimal point in, you can underline it, or you can just imagine 3 sig figs for all of those numbers there. But the reason why it actually works, the reason why you report to that placeholder and the ones placeholder is because think of what 75 grams is implying. It's implying that the plus minus is 1 gram. And so if we're off, if the uncertainty on both those numbers is both off on the low side, then the mass would be 148 grams. And if we're off on the high side, it would be 152 grams. So the plus minus, the uncertainty in both of those numbers is kind of affecting or impacting the one's placeholder. It's impacting this placeholder here. You can see that's where our change is occurring in our math. We'll contrast that with the multiplication rule in a minute. But let's just look at a couple examples before we move off. If I have hundredths place minus hundredths place, then my result should be good to the hundredths placeholder. And so if I throw this into a calculator, 125.6, 0 minus 105.59, I get 20.01. The important thing here is with addition and subtraction, we're not counting sig figs. We're not looking at 5 sig figs minus 5 sig figs is 5 sig figs. We're not looking at 2 sig figs plus 2 sig figs is rounded to 2. It's all about the placeholders. It's all about this placeholder minus that placeholder. We report it to that same placeholder. When I do math, a lot of times I want to line the numbers up on the decimal point so I can see where I'm going to round. If I take 125.05 grams, and I add to that 4.4140, I get 129.4640 grams, but then I want to round this to the hundredths placeholder. So I want to round this appropriately. Now, I round up when it's a 5 or greater, I round down when it's less than 5. There's some silly round even rule that I wouldn't worry too much about. When it's exactly 5, the textbook has some issue, and maybe we should round up half the time, down half the time. Don't worry about that. If it's a 5 or greater, we'll round up. If it's less than 5, we'll round down. So we round this down to 129.46 grams. Now, the issue here in the third problem is getting at like, well, why would you use 2 different types of balances? Like you'll see this in the lab, or maybe you don't. Maybe you've encountered this before, that some mass balances can go to 2 placeholders, some to 4. So if you took one measurement of mass to 2 sig figs, you might as well just have used the same balance for the second object, because you're going to lose those 2 sig figs you gain with the better balance. So the thing that you may be confused at first is, well, how would you have one mass to 2 sig figs, 1 to 4? You have to imagine when you see numbers with units that some device was used to measure those numbers that was appropriate to give you that number, and that the plus minus in the first one is 0.01 grams, at least 0.01 grams, if not greater. And the last one, the uncertainty, is plus minus 0.001 grams. So you're assuming that the last digit you see in the number is the number that carries some uncertainty to it. That's what's leading us to rounding off here. It's the plus minus 001 is a greater uncertainty, so we round off to that placeholder. So it's all about looking at the placeholder, rounding appropriately for addition and subtraction. And then we look at multiplication. It's all about actually counting sig figs. So the multiplication rule is that when we multiply and divide, results are reported to the same total number of sig figs as the value in the problem that has error, that has the least number of sig figs. So we're rounding to the least sig figs. So again, we inspect our numbers. We see ordinary mass measurements. The book will give you just some like examples of ordinary numbers and say apply sig fig rules. If you see a general example without units given, you're just assuming the numbers shown are some sort of inherently imprecise set of numbers. When we get into some calculations that involve conversions, we're going to have to be a little bit more thoughtful of conversion factors aren't making us round. It's just the uncertain and measured numbers representing inexact quantities. But let's think of our plus minus 1 here for the 75, kind of like we did before. So for 75 times 75, that would be 5625 square meters if I just throw into a calculator. And so the issue is, where do I round this to? Well, it says round to the same number of sig figs as the value with the least sig figs. So 2 sig figs times 2 sig figs should be rounded to 2 sig figs. The second significant figure would be the 6. So that would be 5,600 square meters, which does imply 2 sig figs, so I don't necessarily need scientific notation. If I want to invoke scientific notation to avoid ambiguities, it would be 5.6 times 10 to the 3 square meters. And so 2 sig figs. Now first, multiply and divide, you count sig figs. It's actually very easy. because you're just looking at the sig fig counts and dividing or doing the math accordingly and then rounding to that number of sig figs. But you just have to make sure you don't go back to the addition rule and start counting sig figs and applying the multiplication rule to addition and subtraction. So just remember addition, subtraction, all about placeholders, multiplying, dividing, all about counting sig figs. Now, why does this work? Well, imagine 74 times 74. If we're off on the low side, so 74 times 74 is 5476. And imagine if we're plus minus off on the high side, 76 times 76 is 5776. Where's the change occurring? The change is occurring in that hundreds placeholder. Do you see the plus minus, the inherent uncertainty in the numbers, or where they're leading to the errors being in that second significant figure placeholder? That's why we rounded 2 sig figs. If you've taken stats class, you can learn how to propagate the uncertainties and round off with an actual plus minus, but here you're getting that without doing that more formal analysis. So if I have one of them to 4 sig figs, the other to 2, guess what? It's still 2, 5,600 square meters for our second problem here. So still 2 sig figs, so I have 4 times 2, I'm gonna round to 2 sig figs. If I have 4 times 4, then I get to keep all 4 of those digits, 5625 square meters. But again, it's not 5625 with an infinite number of zeros, it's 5625 plus or minus 1. If I do a density problem, 2 divided by 3, 2 sig figs. I won't work out the math, but when we do that, we'll round it to the second sig fig. I just want to allude to the last rule so we can run with this next time. When I do multi-step problems, what I want to do is I want to apply the rules in the order I do the calculations. So if I add numbers, I want to do the addition rule. When I divide, I want to do the division rule. So I want to think, when I add and subtract in a problem, I apply that rule. When I divide, I apply that rule. Oddly, we try to round only once in the problem at the end. That was kind of part of your lab right assignment. We'll look at that next time in some examples on how we can generally try to round just once, but tracking sig figs, applying rules sequentially as we go in multi-step problems. So we'll be in the chapter 2 next time after we wrap up chapter 1. So the chapter 2 slides are posted up on Carmen. That'll do us for today. Have a great day, and I'll see you on Friday.